Okay, so I hope you watch this TED Talk and you have a better idea of what a wave packet is and how the uncertainty principle works. And most particularly, that the uncertainty principle is not anything to do with who's measuring it. It is just a limitation of the universe that we will never get around, as far as we know. Okay. The next piece of this puzzle comes from actually a mathematician, a statistician, so somebody who studies statistics. And basically, a lot of people on the internet are familiar with Schrodinger because they talk about Schrodinger's cat, and they think that Schrodinger actually, like, murdered cats or something. And I want to tell you that that is not true. It was a thought experiment that he used to try and illustrate his math. Okay, so he had this really complicated mathematical equation with so many layers. As a chemistry major, it's not until your third year in college that you are prepared to even interact with this equation. But he was trying to explain this complicated math to people and essentially also explain the uncertainty principle at the same time. And essentially what it is it's in your head, not for real. Don't do this. He didn't. You shouldn't either. But you put a cat in a box, and the box contains a sealed container of a radioactive isotope. And radioactive isotopes decay individually, anyway, at a random time. So you can never predict when any given atom of a radioactive isotope is going to decay. But at some point in time, it will. And so his theory was, or his idea, his proposal here, his thought experiment, was if we have this cat in the box, and at any time the radioactive isotope might decay and be released from the container when that decay happens, then the cat could be at any time dead. But also, because we don't know when that decay is going to happen, the cat could be at any time alive. And so that's Schrodinger's cat experiment, right? He's just trying to articulate uncertainty and how we don't know what's going to happen or when it's going to happen. Electrons are the same way. We don't know exactly where electrons are at or when. So we have to make some probable guesses. And that's where statistics comes in. So Schrodinger's approach was to take statistics, population dynamics, and apply it to electrons. And that had never been done in science before. It was a revolutionary idea. But when he did, he came up with this equation. This has so many layers of equations built into it. You can spend an entire semester, in fact, chemistry majors do, studying this equation and what it means. Basically, it also gets you the line spectrum of hydrogen. So it agrees with the Bohr model, which is good support for the Bohr model. But then it also allows, with a lot of work, it also allows you to calculate the line spectrum of other elements. Okay? So you're not going to interact with this at all. I just wanted you to see it. Each one of these, so this is an eigenvalue is what that's called. And so that's a mathematical formula that you would put into. This is a psi value. That's another math formula. This has to do with distance. So electrons depend on distance. So that part makes sense. This is Planck's constant. And it just goes on and on. Every single variable that you see is actually another equation that gets plugged into this equation. Psi is called a wave function. And it doesn't actually mean anything. It just has to do with the math and the way that it works out. But it turns out, so you get -1, square root of -1, that kind of complex number ends up in there. In other words, if you're in math right now. But as it turns out, if we take the value of the wave function and square it, that will give us the likelihood of finding an electron in a particular location relative to the nucleus. It creates some interesting three-dimensional shapes. It's not just the orbitals that Bohr created. It has different probabilities in different directions from the nucleus. So we call them orbitals. And let me show you a little bit about orbitals, because they are the foundation of quantum mechanics. All right, so quantum mechanics starts with the quantum number n, which we already talked about in lecture. That is essentially, for the main group elements, equal to the period number. So if you use your periodic table, n can be anywhere from 1 to 7. That's the foundation of everything. Every period also represents a collection of subshells. Okay, so we have up to 7 different subshells that electrons can be in. If you want to calculate the total number of orbitals, you can take n and square it. So the highest value we can have is 49, because 7 squared is 49. We can have a total of 49 different orbitals. That is 49 different shapes and locations and directions that electrons can exist in. Don't worry, we don't have to memorize all of them. The periodic table is going to help us out a whole bunch. So don't get too stressed about this. I'm just giving you the background, and then we're going to use the periodic table as a tool to help us write all these different quantum numbers down. So n is period number for the main group elements. And again, that's groups 1 and 2, and then 13 through 18. As it turns out, the transition metals, so again, that's 3 through 12. The transition metals will be the n is equal to the period minus 1. And our actinide and lanthanide series down at the bottom of the periodic table, n is equal to the period number minus 2. So these are just some facts to keep in mind as we go forward. I'll show you how this relates to the periodic table in a minute. Once you know your n value for a given electron, you can figure out what angular momentum numbers it might have. So let's just go through an example here. You're going to want scrap paper or print out your notes. If we have, I'm going to put it in purple here, if we have a value of n equals 3, so it's some element in the 3rd period, then we can anticipate what values of L, this is an L by the way, not a 1, we can anticipate what values of L it will have. And once we figure that out, we can figure out the shape of the orbital, which tells us a lot about how the molecule is shaped in the next chapter. So if we calculate a value of 0, the shape is what we call an S. This one's an easy shape to remember. It's a sphere, like a hollow sphere, a shell. If you end up with an L value of 1, it has a P shape. I'll show you a picture of that in a second, but it's kind of like if you take 6 balloons and hold them all together in the middle. If you get an L value of 2, you have D orbital. These have complicated shapes. I'll show you them in a minute. And if you get a value of L of 3, you have an F orbital, which has even more complicated shapes. So they get more complex as we go up the list here. So just to walk through how this works. If we had an electron with an energy level of 3, its possible values of angular momentum are anywhere from 0 to n minus 1. So we're going to say that L is 0, 1, or 2 for this particular electron. So that's where the electron is allowed to go relative to the nucleus. So 0 would be an S orbital, 1 would be a P orbital, and 2 is a D orbital. So anything in the 3rd period cannot have an F orbital shape. Okay? The next value depends on L. So our magnetic quantum number, which is designated as a lowercase m with a subscript L, is based on which of these shapes something takes. So I'll just choose, I'll pretend like this particular electron was in a D orbital. So I'm going to go with L equals 3. If that's the case, then we have a lot of choices for which magnetic quantum number it can have. It goes all the way from negative L to positive L. So we're going to go negative L would be negative 3. Only whole numbers here. Don't forget 0. 0 is a number as well. Okay, so it goes all the way from negative L up to positive L. Oh. So I'm going to choose L equals 2 here. And so we're going to go all the way from negative L to positive L. So negative L would be negative 2. And we're only going to do whole numbers. And don't forget 0. 0 still counts as a number. So these are all the magnetic quantum numbers that an electron in a d orbital, so L value of 2, might have. You'll notice there are 5 total options. So later on, we're going to learn that within a d orbital, there's 5 boxes that you can put electrons into. The last variable is called the spin quantum number, and it's pretty simple. For each electron, it can either be a spin basically clockwise or a spin counterclockwise, and that's it. Sometimes we refer to the spin as up or down. In reality, physically, it's none of those things. It's not clockwise or counterclockwise or up or down. It's just a matter of what direction the magnetic field goes, and magnetic fields are generated when objects spin. So even though we can't see the electrons themselves, we know they must be spinning in one direction or the other. All right, and so essentially, if we say took, the m sub L of plus 2, within that one, we get a plus 1/2 spin and a minus 1/2 spin. So every m sub L can contain 2 electrons. So every box can contain 2 electrons. We show them as arrows, where one spins up and the other one spins down. So that's a very brief introduction to the quantum numbers. You should try to be familiar with these concepts. They're going to come up on your final. But when you read the textbook, you can find further details if you need it. What they lead to, though, the mental picture that is the most important part here, is the fact that if you solve psi squared from Schrodinger's equation that I showed you a bit ago, the complicated one, you get this distribution of probability. So each peak represents, the highest part of the peak represents where you are most likely to find an electron. 0 represents the nucleus. And so this is the explanation for why electrons don't fall into the center, because as it turns out, every time you solve Schrodinger's equation, the probability of finding an electron at the nucleus is 0. So wherever we don't find electrons, so 0 probability, we call that a node. So here you can see for the energy level 1 with the angular momentum of 0, so that leaves us with an S shape, which I told you a second ago was a sphere. That has only one average position and only one node at the beginning in the nucleus, right? So this tells us that there is just one shell around the nucleus where electrons could exist if you're in the 1s orbital. If you're in a 2s, you still have the 1 in the center, and then you have this big empty space. That's a node. So this is your node right here. Here's your nucleus node. This node, no electrons are allowed to go into, but then we end up with a probability in this green area of having a lot of electrons, or a much higher probability of having electrons be present. We want to remember each one of these can only hold a maximum of 2 electrons, spinning up or spinning down. That's all. So you can fit 2 electrons in the pink sphere, and you can fit 2 more electrons in the green sphere, but weirdly, they cannot exist in between those places. This does not make sense on a macro scale level. When you think about how a person travels from point A to point B, you have to exist in between. But electrons don't. They literally disappear from one energy level and appear in the next one. And that's weird. Okay? And so as we keep going, we find more nodes. So when you get to energy level of 3, like our example, you have the node at the nucleus still. You have the node between energy level 1 and energy level 2, but you also have another node between 2 and 3. Okay? So this explains why electrons have to be discrete energy levels. It explains where they are at in an atom, and it explains why they don't fall into the nucleus. So we have solved some mysteries with this. I promised you I would show you what p orbitals look like. Here it is. So imagine each red one is one box, and you can fit one electron here and one electron there. Same thing for the green. You can fit one here and one there, and one here and one there. And they can jump between the p orbitals and the s orbitals, but not exist in between those shapes. So in real atoms, you have s orbitals overlapping with the p orbitals in physical space, but not in energy. And so for electrons, energy matters more than physical overlap. If things are not in the same energy level, they can't jump between them unless you add or take away energy. Okay, so it's really interesting.